exercise 44 on section 14.7. It's actually a quite complicated exercise. It's not easy. It's not an easy one. We are asked to find the points on surface that are closest to the origin. The surface is given by the equation y squared equals 9 plus xz. Alright, so it's not so hard to verify that it's a surface. That is, if you look at the, so this is essentially the set of point x, y, z such that y squared minus 9 minus xz equals 0. So if you call this function capital H of x, y, z, you are looking at a level surface, a level set of the function h. I claim that for all points satisfied in R3, the gradient of h or the differential of f never vanish. Let's say the partial derivative with respect to x, y, z do not vanish at the same time. That's what it is. All right, but that's not pretty much what we want to do. We have to minimize something. What is to minimize? We have to minimize the distance between the origin and a point x, y, z that satisfies this. Well, minimizing the distance amounts to minimizing the square of the distance. So I'm going to consider the square of the distance. Well, if I consider the vector formed by this point and the origin, the square of the norm of this vector is given by this. So this is the function I have to minimizing, requiring that this holds. Well, if this holds, that I can replace y squared by 9 plus xz, and the function now to minimize is this one. Now, we need to see where is the domain I'm going to look at. And I claim that this domain is certainly not bounded. You see, you can take values of xz very large, values of xz very large, right? And you get values of y quite large, so this is not a bounded domain. Right. There is one thing though that this is not going to be defined for all values of xz. I mean, there are certainly values of xz when xz are positive. That makes sense, no problem. But you see, since y squared has to be positive, definitely what we cannot have is 9 plus xz to be negative. So xz is always bigger than minus 9. Making what? The domain on R2 that I'm going to consider is this one. So xz should always be bigger than minus 9. What does it mean? That means that, okay, well, I'm drawing those hyperbola. So this is z equal at minus 9 divided by x. X equal minus 9 divided by x. We have two hyperbolic branch. And the domain under consideration is exactly this guy here. I can't get here for values of x which are here or here in such a way that the product of x and z is less than minus 9. So we have to be pretty much here. Well, the origin is perfect. That's no problem. xz will be bigger than will be equal to 0, so it's bigger than minus 9. That's no problem. All right. So the theory tells us that a global mean, if there is a global mean, it has to be reached either inside the domain as the image of the critical point, or at the boundary of the domain. So it could be here, here, or here. My global mean. Does this global mean exist? I said yes. So if you look at the limit of f bar of xz as xz tends to infinity, well, we have infinity. Where can xz tends to infinity? It cannot tend to infinity on those sides, but it would tend to infinity on this side. And then I know that xz will be always positive here on those sides, and this is always bigger than x squared plus z squared. And so this is really tending to infinity. So now I can apply a theorem says, well, I could have a global mean at the boundary here, right? Or it could be inside the domain. So actually we will see that we will see that we're going to find only one critical point for this map. We'll see where it's located. And we will need still to study the behavior of this function f hat on the boundary. So that means that we'll have to replace z is equal to minus 9 over x and to study the variation of this function. So it's somehow a lot of work. To be honest with you, if I were to give you this this exercise, I would probably simplify the exercise. Says we're going to assume that the product x z is always positive, so that those two things won't be under consideration. All right, fine. So now let's look at the critical point of this function. So I need to erase a few things here, guys. I know that this is true, and I'm going to erase the top here. I don't need it anymore. I don't need this anymore. I don't need this anymore. All right, and I don't need this anymore. All right, so let's first of all discuss the critical point of f. df hat over dx is equal to what? Well, 2x plus z, and df hat over dz equal 2z plus x. So for those two things to be equal to 0, well, I claim that there's only one point that satisfies this, is just the origin. Well, you can verify this if z is equal to minus 2x from this expression. Replace z in this, and you see, a minus 4x plus x equals 0. Well, that means x have to be equal to 0, and if x is equal to 0, z has to be equal to 0. So we have only one critical point located at the origin. What is the correct, so the CP's equals 0, 0. What is the critical value, right? Well, the critical value, you know, that x and z equals 0, I have f of 0, 0 equal 9. If it were, if this point would be the right candidate for the minimal distance between so if this value is really the minimum distance, which value, which point on the surface does it correspond? We know that x equals 0, z equals 0. What about y? Y squared equals 9 plus xz. So y squared equals 9, so that means that y equals 3 plus or minus. So it means that we would have 2 points, 0, 3, 0, and 0, minus 3, 0, for a distance being equal to 9. All right. But it's not over yet. As I said, the minimum could be obtained also on the boundary on this domain. Well, it won't be obtained for, let's say, values of x, y, for x, z, let's say, on the asymptote, because one of them, you know, as I said, so one of them, one of x or z, will be tending to infinity, the other one tends to 0, it doesn't matter. But so this would certainly not obtain for let's say for values of x and values of z close to 0, or values of x and z close to infinity, certainly not. But it could be somewhere in between, who knows? All right, so we need to study now another map. So I'm going to call it G of x only, where I replace z by minus 9 divided by x squared. So it's going to be x squared plus z squared, that's 81 divided by x squared. And this quantity goes in the trap. 9 plus xz goes in the bin. Right, so what is the minimum value of this function when x belongs to R minus the origin? I can't take the 0 here. So the last part of my study, I need to be complete because I cannot avoid this. Let me erase this. I need to go back to calculus y, in other words, and study the variation of this function, x squared plus x1 or x squared. Well, okay, so as I said, the function, the map is defined everywhere except at 0, so I have a double bar below 0. I need to study the variation of the function. So g prime of x is equal to 2x minus 281 times x third, using the general power rule, right? which means that this is equal to 0 if and only if, you see, what is it? X fourth equal 81. And therefore, x equal 3, or plus or minus 3. So, okay, so I got two critical points, minus 3, 3, 0, 0. And what is the behavior of the function? It's easy to verify that this is decreasing and then increasing again. So this is going to be actually restricted to the boundary. We're going to get here a mean. Same thing here, because the function is completely even, so we're going to get exactly the same thing. Now, what we need to do is to compute, of course, the critical value. And the critical value, hopefully, and that's what we have to compare with the other one. So the critical value, what is g of 3 or g of minus 3? This is exactly the same. It tells you it's 9 plus 81 divided by 9. So it's 9 plus 9, so it's 18. And that's the minimum distance f can get onto the boundary. Well, but this minimum distance, nevertheless, was certainly bigger than the minimum distance I get at the origin. So if I compare the minimum restricted to the boundary of this domain, this branch and this branch, and the image of the critical point, this critical point is giving me the smallest critical value. And therefore, these are the 2 points we were looking at. All right, so the difficulty of this exercise actually is to set up the problem correctly and not to forget that we have actually that we are not looking at a function depending upon x and z defined everywhere. No, it's not defined everywhere. We have a restriction that x times z cannot be negative because x times z plus 9 equals y squared, and therefore, since y squared is always positive, xz has to be always bigger than minus 9. So that means that these are the boundary of the domain we are considering. But the principle is the same. I'm still looking at the location of the critical point inside the interior of this domain, and I need to study the behavior of the function at the boundary. It could be that, we get a global mean by just going around here. Actually, it's not the case. We got some, let's say, I will say along the boundary, some local minimum, which is 18, but this local minimum turns out to be bigger than the image of the critical point. That's it.